A modern global supply chain or a financial portfolio doesn't operate on a few manageable metrics. They are driven by millions of simultaneous variables, shipping routes, fuel costs, asset yields, that compound well beyond the limits of human calculation. Managing this volume of data requires stripping away the noise to find the most efficient path to maximize returns or cut waste down to the fraction of a cent. But a volatile physical operation cannot be optimized until it is translated into a strict, static algebraic architecture. This mathematical translation is exactly what optimization software is built to execute. LINDO has been a standard-bearer in operations research for decades because it abstracts the heavy algorithmic lifting away from the engineer. It acts as a processing engine capable of computing linear, integer, and nonlinear programming scenarios. We are going to reverse engineer this optimization pipeline to see exactly how real-world physical chaos is mapped into a solvable constraint matrix. An optimization solver provides the structural bridge that turns physical business realities into deterministic mathematical solutions. Before a single calculation occurs, the solver requires a mathematical environment that matches the reality of the operation. Different physical environments demand distinct mathematical assumptions. The most common environment is linear programming. This handles continuous variables, meaning the data can be divided into infinitely smaller fractions. We visualize this continuous environment as a smooth plane. It's ideal for calculating fluid volumes, where producing 100.5 liters is valid. But for integer programming, it shatters into a discrete grid. The solver requires variables to be absolute whole numbers. This is required for discrete resource allocation, like assigning specific whole machines to a floor. Mixed integer programming generates a hybrid space where smooth planes intersect directly with distinct coordinates. For quadratic relationships, nonlinear programming warps the topography into complex, curved surfaces. An analyst's first critical choice is selecting the correct topography for the software engine to navigate. Applying a continuous linear algorithm to a discrete integer problem yields useless answers, like instructing a factory to assign exactly 2.4 workers to a shift. Choosing the wrong topography forces the solver to optimize a reality that does not actually exist. To see how a physical limitation becomes an algebraic model, we can look at a specific industrial application, like a manufacturing plant. Every optimization tool requires a highly specific syntax to function. This begins on the right side of the screen with the definition of decision variables. These variables represent the exact moving parts the software engine is allowed to control, like deciding the ratio of products on an assembly line. Next comes the second architectural step, writing the objective function. The objective function acts as the singular mathematical goal. Here, we instruct the software to maximize total profit, represented as Z. Once the goal is set, we move to the most rigorous step, adding constraints. Constraints translate absolute physical limitations on the left, like maximum labor or materials, into strict algebraic inequalities on the right. The software has no independent knowledge of the factory. It relies entirely on the mathematical precision of these greater than and less than signs to define what is physically possible.
If an analyst misses a single real-world constraint, like a scheduled machine maintenance, the matrix is compromised. The algorithm will generate an optimal command that is physically impossible to execute. With the variables, objective, and constraints fully defined, the LINDO solver engine takes over to execute the calculations. We can see on this coordinate graph how the engine visualizes the math. It plots the constraint equations as intersecting boundary lines on a geometric plane. This shape is the feasible region. Every point inside is a valid decision satisfying all constraints. The engine evaluates the objective function against this space, searching for the maximum value. The optimal solution rests on the extreme edge or vertex of this region. This deterministic algorithmic calculation happens in fractions of a second, automating a process that would take a team of analysts weeks of trial and error to approximate.
Yet, isolating this optimal vertex is not the end of operations research. It provides the mathematical baseline required for true strategic analysis. There is an inherent flaw in that calculated optimal vertex. It assumes the physical environment will remain completely static. Real-world operations are volatile. A sudden drop in labor availability or an unexpected delay in the supply chain instantly invalidates those static assumptions. To address this dynamic volatility, optimization software includes comprehensive modules for sensitivity and what-if analysis. Looking back at our graph, sensitivity analysis is the process of testing exactly how much a parameter can deviate before the boundary line shifts inward, forcing the original vertex to jump to a new optimal point. This post-optimality review reveals the hidden vulnerabilities in a business strategy. It quantifies exactly how robust the current solution is against market fluctuations. Engineers can also use what-if analysis to deliberately alter coefficients within the model, running simulations of worst-case scenarios to observe the potential impacts on the system. The resulting reports generate precise mathematical ranges of tolerance for every moving part in the operation. Effective decision support quantifies the exact mathematical boundaries of a system's resilience against chaos. Pulling back from the software engine itself, it becomes clear that mathematical solvers do not operate in a vacuum. To maintain the quality of their input data, solvers must integrate directly into broader business analytics workflows, pulling parameters straight from SQL databases and Microsoft Excel. Today, the architecture of optimization is rapidly converging with Industry 4.0 trends, specifically the integration of big data and AI-assisted analytics. This leads directly to the concept of the digital twin. This is a real-time digital simulation of the physical operation that feeds live parameter updates directly into the mathematical constraint matrix. While continuous data feeds and machine learning increase computational accuracy, they do not replace the human understanding required to manage the system. Algorithms lack real-world intuition. They only optimize the literal parameters they are coded to respect. Generating a reliable, actionable operational strategy depends on domain expertise to identify which variables matter on the factory floor and which constraints are physically unyielding. In the architecture of modern decision-making, the solver engine dictates the math, but human domain expertise dictates the reality.